Okay, so we've already talked about Newton's first law and second law as it relates to momentum, but now we're going to talk about Newton's third law as it relates to momentum and its conservation. So let's get started. Newton's third law, as you know, is nothing but action and reaction forces. So it says that when a body exerts a force on another body, then the second body also exerts an equal and oppositely directed force on the first body. So equal and opposite forces. The force that the first body, so maybe this little blue body over here, exerts on the second body, see it's exerting a force this way, is considered the action force. And the force applied by the second body, so this little red body over here, is also pushing with an equal but opposite reaction force. All right, so we've been talking about collisions, and we're going to talk more about collisions between two objects. So when in a collision, both objects experience forces that are equal in magnitude in opposite direction. So these forces that they experience can cause the object to maybe speed up, so that's gaining momentum, or it can cause the object to slow down or lose momentum. But according to Newton's third law, the forces on the two objects are equal in magnitude. So they're equal forces. Wouldn't they just cancel each other out? But no, that's not the case. While the forces are equal in magnitude in opposite direction, the accelerations of those objects are not necessarily equal in magnitude. So even though it's equal in opposite forces, the accelerations are still different for the object. Because remember, according to Newton's second law of motion, we had this handy-dandy equation to represent the second law of equation. Newton's second law of motion. So it says the acceleration of an object is dependent upon force and mass. So although the forces are equal in magnitude and opposite in direction, the acceleration will be different because the masses of the object. So if the colliding objects have unequal masses, so maybe this is 2 kilograms and this is 10 kilograms, then of course, even though they have equal and opposite forces being applied towards the opposite bodies, they would still have unequal accelerations because their masses are unequal. So let's take a look at a golf example. So here's a club head, a view from a club head, and then a golf ball. So there is a rightward moving club head going towards the right in order to hit the golf ball, right? It experiences a leftward force, and that leftward force is coming from the golf ball. So in the moment that they do meet, they are interacting with each other. The club head is producing that rightward force. The golf ball is producing that leftward force. And remember, these forces have equal magnitude and opposite in direction forces. So the force felt by the club head is equal to the force experienced by the golf ball. Equal and opposite. Most observers of this collision have difficulty with this concept because they think that the high speed given to the ball as a result of the collision, they think it's because there's unequal forces. But really, you're not observing unequal forces upon the ball and the club head, but rather unequal accelerations. Both the club head and the ball experience equal forces, equal and opposite forces, Newton's third law, yet the ball experiences a greater acceleration due to its smaller mass. So you have equal and opposite forces, but you have unequal masses, and that's what causes your unequal accelerations. All right, and bringing it home. So there is a law of conservation of momentum, and this law says that in an isolated system, so in this isolated system, we're not considering friction, we're not considering air resistance, we're not considering other factors. But in this isolated, perfect little system, the total momentum does not change. So that means that momentum is conserved in all closed system collisions. And I will go ahead and tell you now, in our class, we are pretty much only going to be looking at closed systems. So, momentum is conserved. That's the big idea. Momentum is always conserved. So that means if you start with 20 units of momentum before the collision, then after the collision, you will still have 20 units of momentum afterwards. Momentum is conserved. We're not losing it, we're not gaining it. It stays at 20, or it stays at 40, or whatever it was to begin with. All right, thanks for watching. That's it.